Hi everyone, welcome to our event. This event is brought to you by Datadog's Club, which is a community of people who love data. We have weekly events, and today is one of such events. If you want to find out more about the events we have, there is a link in the description. Go there, check it out. We have quite a few events in the pipeline, a lot of workshops. For some reasons, a lot of stuff about LLM lately. I don't know if it's a coincidence or not. I think we have like 2 more events about LLMs, one workshop and one webinar. So check it out. All of them are amazing. Like the event we are going to have today. Then do not forget to hit the subscribe button. I think I need to update the screenshot here. It's a lot more subscribers. But if you don't want to miss out on the future events that we will have, don't forget to subscribe. And we have an amazing Slack community where you can hang out with other data enthusiasts. During today's webinar, you can ask any question you want. We will be covering these questions at the end of the presentation. So ask your questions there and we will answer them. And right now I'm going to stop sharing my screen. And Nikita, the floor is yours.
Great. Thanks so much. Very, very happy to be here and share some of my experience working with LLMs and in particular with retrieval augmented generation chatbots. This is the thing I will be talking about today. Let me start sharing my screen. Are you able to see the slide deck now?
Yes.
Great. Right. So what I will be talking about is 5 techniques for improving RAG chatbots. If you don't know how RAG chatbots work, don't worry. I will first start by providing a brief intro and explaining to you what I mean by that. And in particular, in the talk, we're going to focus on improving the retrieval part of those chatbots. And as you will see, the retrievers are the key component of those conversational assistants, and improving them can help a lot to build the high quality assistants that can accurately answer your questions. So before I start, just a few notes about myself. So my name is Nikita. I currently work as applied scientist at Amazon Web Services, where I'm working in a team that builds generative AI solutions for different customers across different industries. So customers come in to us and we try to develop the prototypes, the proof of concept solutions for them to unlock different value that generative AI can build to some of the use cases that the customers have. Before joining Amazon, I have also been doing my PhD at Humboldt University of Berlin, where I focused mostly on ML for credit risk analytics. And I also used to spend quite a lot of time on Kaggle doing different competitions from different domains. So in a few years of doing Kaggle, I managed to earn 18 medals in different competitions. Of course, most of them not gold medals, but still it was very nice to get exposure to a lot of different problems. I'm not doing that much of Kaggle anymore because I have a lot of other things going on, but that was also a nice page in my history, so to say. And just to also give you a quick few words about our team at Amazon before I dive into the topic. The team I'm working at is called Generative AI Innovation Center. And this is a customer-facing team, meaning that we work not on internal Amazon products, but we work with external customers, business customers who come to Amazon Web Services for consultancy or for some support in implementing different solutions. And what we try to do with them, as I was mentioning earlier, we try to identify use cases that can be solved with generative AI, with LLMs or with other models that can help in that domain. And then we build proof of concept. So we build first prototypes for the customers so that they can take them and implement them into production, and we support them on the way to production. So this gets us working with many different customers from many different industries, and this is how I was also able to get some experience working with those models as well. So if you are interested, check out our Amazon.jobs website. There are some positions available across different European countries and other countries as well. So check it out, and if you're interested, apply to work with us. Great. So in this talk, I will first do a quick intro to RAG chatbots to explain to you how they work so that we all have the same understanding about those systems. And then I will talk one by one about 5 techniques that are based on my experience and based on experience of other people that you can find in different papers or blog posts as well, are crucial to improve the quality of the chatbots and the quality of the retrieval components of these chatbots. I think maybe the main thing I would like you to get out of this talk is that when we think about those conversational assistants with this new generative AI domain unraveling, we may think that you just plug in an API call to a big LLM and this solves your problems. But this is actually not the case. This is only one part of the big system that you need to set up, and there are many places in the system where you need to work actively on implementing different iterations and different improvements, very much similar to the classic ML world. So it's not solved just by feeding your user questions from the chatbot to a language model API. There are many things you need to build on top of that, and I hope that while I am discussing those techniques, you will get this understanding during the webinar as well. Okay, so first of all, what are the RAG chatbots? So the word RAG stands for Retrieval Augmented Generation. It may sound a bit fancy, but what it means in simple terms is that instead of just generating the answer, we are also having some retrieved context that our language model can see when it generates the answer. So this is just about augmenting what we send to a language model with some of the additional context that we may have retrieved from a certain database. Before we dive into that, let's think why are these conversational assistants are needed in the first place. So when we think about them, the classic way we used to do this before is to have simple search, right? So if you can go on internet and use one of the popular search engines, this is how you would usually go about it. So let's say I have a question. What is self-attention? I will use this example throughout the talk. And we want to know what self-attention is. So if you use classic search experience, what you will get in response, you will get a couple of sources that talk about attention. And then you can click on those sources, you can go check them out, and you can get the answer for yourself. This is how it used to work previously without chatbots. What you can do now with those conversational assistants is that in addition, or mainly instead of getting you just the search results, just the links that you should click on and check out yourselves, you would actually get a direct answer. And this is what we want to achieve when we have a conversational assistant, right? It may provide you a link that you can also click and get deeper into the document yourself. But the main thing is that it will also be able to provide you a direct answer on your question. And this is the main reason we want to build those assistants, because we want our users to save time. We don't want them to click in and manually reading through those documents. We rather want them to have a direct answer that they can double check if needed, but that they can rely on instead of having this need to browse through the sources manually. And when we think about those conversational assistants, there are essentially different ways to implement them. But in a nutshell, given the modern state of generative AI, there are 2 ways you can go. You can do it without any RAG, or you can do it with RAG. If you do it without any RAG, it's a simple API call to a language model, right? So if we ask what is self-attention, we can just simply send our question to the language model, and the language model is learned to generate text in response to text, so it will always provide us some kind of an answer, right? And for many generic and easy questions, this will work out of the box, and there is no need to go beyond that. But then the problems start to occur when we try to ask more specific questions, or questions about things that are more recent and might not have been included in the training data of those models. So imagine there is a new paper comes out that introduces a new mechanism, and if we start asking one of the language models about it, you will not get a reasonable answer. The model will hallucinate something, right? Because it doesn't know this information, because this information hasn't been part of the training data of that model. Or imagine that we are, as a company, maybe we are a retailer who sells smartphones, and we want to build an assistant that can answer questions about our smartphones. But if the data about our smartphones has not been used to train the model, this model will never be able to answer those questions correctly. So what we want to do, we want to teach the model to so that it knows about this data and so that it can handle those questions also accurately. And this is what is usually solved with RAG. So what RAG means is that now, in addition to the generation part, we also add the retriever component in the middle. So before we actually ask a language model, we will have a retriever that will retrieve relevant data, relevant text context that we can also show to the LLM before it answers the question. So imagine we have this database with our smartphone product descriptions. Now, before we answer the question, we can actually fetch a description of a smartphone from our database, and then together with our user question, send it to the large language model. And then the model will be able to reason about it because it has seen the text that describes the product or the phenomena that we wanted to answer. This is essentially how it works. I think it's easy to think of this as open book and closed book exam, right? If you do it with no RAG, it's like coming to exam and just trying to answer based on your memory. But if you skipped a couple of lectures, maybe you don't know what the question is asking for. So you will try to come up with something, but that may not be accurate. And in the open book exam, you have a textbook, right? So given a question, you can go through your textbook, you can find a place, or maybe you can find like a slide that explains this phenomena, and then you can use this slide as a context when you are providing the answer to your question. This is why it tends to be more accurate, and specifically in the cases where this data that we can get from this textbook is not possible for the model to see beforehand. So this is why we need RAG systems, and this is on a high level how they work. So in this talk, I would like to focus more on the retrieval part of that system, and I can explain why. You probably have heard about the phrase garbage in, garbage out, which is very common in machine learning, and it usually refers to the cases when if we feed bad training data to our model, we'll probably get bad predictions in return as well, because bad data produces bad predictions. This is a bit similar in those systems as well. So if we come back to our example of an exam, if I'm coming to an exam and I don't know nothing about the topic, but when someone gave me the notes, but they just made up those notes, those notes are wrong. They're saying that, self-attention is a procedure when people need to meditate and think about their inner self or something like this. And if, I don't have any other information, I will just use those notes and answer the question incorrectly. But if those notes are good, if those notes are very clearly saying, okay, self-attention is this mechanism that is used in deep learning models and so on and so forth, then I can just, copy paste those notes, maybe rephrasing them a little bit, and I will be able to come up with a relevant answer to my question. So there are a couple of studies who, quantify the specific accuracies and improvements based on whether or not you have a good retriever or not. But on the intuitive level, if you have very good notes, even if you are not that smart yourself, or if you as a language model are not, very big model, you haven't seen a lot of data, you haven't seen the whole internet. So even if you are having a smaller model that is a bit less capable, you will still be able to answer correctly because you saw the good notes. You can just immediately produce the answer. If you don't see the good notes, if you are very smart, so if you're a very big model, have been trained on a lot of data, maybe you will be able to come up with reasonable answers, but not in all cases, right? So this is how you can think about it. And this is why improving the retriever is sort of key to improving how those RAG chatbots work. And this is why I wanted to, focus on that part, because this is the part that if we can fix that and make sure that our language model always gets the relevant page of our textbook when it needs to answer the question, we will come a long way towards making those answers high quality and let the LLM take care about the phrasing of the question or finding the relevant paragraph on that page to answer that question. So this is basically how those systems work. Right. So Now, before we go into different techniques, I want to stop and take a little bit deeper look into how this architecture works. So this is a high-level diagram, but I think we need to maybe mention a couple of steps before we jump to the technique, so that we have the same understanding about the components. So when we are building our RAG system in for our use case, we usually have two stages to cover. The first stage is the indexing stage, where we actually ingest those documents. So this is the stage when we write our textbook with notes before we come to the exam. And then the second stage would be the actual exam, when we answer the questions. So when we index the data, let's say, in our case, since we are asking about self-attention, our documents are probably papers or blog posts that talks about machine learning models and deep learning and NLP in particular. So what we need to do is we need to take those documents and parse them into the text files, right? So let's say we have 10 PDFs with different papers. We convert them to 10 TXT files that contain the text content from those documents. Those documents are likely to be big, maybe 20, 30 pages papers. We cannot work with them as is. So what we do is we split those documents into chunks of text, right? The length of the chunk is a parameter that we can decide on, but you can think about different paragraphs, let's say, of the document. So let's imagine that we split every paper into a series of paragraphs that we can work with. And now what we can do now with those paragraphs from across those 10 documents, we can embed those paragraphs using an embedding model, right? This can be a very simple embedding model like Word2Vec, but of course nowadays people don't usually use Word2Vec. They usually rely on the specifically trained transformer embedding models that are popular in the NLP domain. And essentially with that model, you can convert your paragraph of text into a vector of numbers that you can then store in your database. And this is what you need to do to prepare your data for the RAG system. This is how it works. So you go from 10 documents to, let's say, 200 paragraphs, and each of these paragraphs is embedded in a vector. And now when we actually come to the exam and we get to answer the question, what is self-attention? What we can do with that question, we can embed this question into a vector as well. So we again transform this question to a vector of numbers. And then given this vector of numbers, we can now search in our vector database, what are the top K closest chunks of text in the embedding space, right? Because each paragraph, each chunk is now a vector. So we can simply find what are the nearest neighbors of that vector compared to the question that we got asked. Let's say we select top 5 chunks of text in the embedding distance. And this is the top 5 chunks that we will show to our LLM as notes. So we will say, okay, the user asked the question, what is self-attention? Here are the 5 chunks of text that our retriever has returned as most relevant. Can you now answer this question? And this is when LLM will try to answer this question, not only having the user question, but also having those top K chunks that we inserted into the prompt. This is how it works end to end. And this is where we can conclude our section about description of the RAG chatbots, and now jump into different techniques, focusing on the retrieval part of that, how to make sure that we actually show this top K relevant chunks to the LLM. How do they make sure that we find the suitable text pieces? The first thing I would like to talk about is called, there are different names for that in the literature, but one of the names is small to big retrieval. Let me explain the problem that we are trying to solve here. So it has to do with the length of those chunks, with the length of those paragraphs when we split our documents into the texts. Since this is a parameter, we can arrive at any point on a big scale, right? Like in the example on the left side of the slide, we can embed a very long piece of text. Let's say we embed the whole section, which is a couple of pages of the document. On the other hand, we can also split it almost sentence by sentence and embed each sentence. So we can have from a single document, we can have 10 chunks or we can have 1,000 chunks. It's our decision to come up with this number. The problem is that if we use a very long chunk size, so let's say we use the whole section, when we will embed those chunks, we will probably have too much noise in this embedding. So when given the question, what is self-attention? If you look at the left chunk on the slide here, it contains a lot of text. It does mention attention a couple of times, but it also mentions a lot of other concepts as well. And it may be that this piece of text will not be very close in the embedding space to the question that we are asking, because it talks about many different things. So if we have our chunk sizes that are too big, then we will probably not be able to retrieve the relevant pieces, because the relevant information is sort of gets lost since there is a lot of things that are being discussed in a single section of the paper. On the other hand, if we do it on a sentence level or maybe 2 or 3 sentences, we will probably get this chunk if it talks about attention when we also ask about attention. So we will probably have a very good recall. The problem is that given this 1 or 2 sentences, if we provide this as notes to our language model, it will not be able to formulate a very good answer. Like if I gave you only this right chunk that you can see on the slide, you would still not be able to answer what attention mechanism is. You see that they have become an integral part of sequence modeling, but it doesn't tell you much about how does it work. So in that sense, you would still need to be able to rely on more information. So this is a problem because if you include too much, you may not find this chunk. If you include too little, you find this chunk, but you don't have enough context. So one of the ways to solve this problem is to use actually both and start with small chunks and then go to the big chunks. I will explain you what I mean here. So let's say we have our question, what is self-attention? And we try to look through our document. Let's say for simplicity, we have 2 sections in the document and we have 3 chunks, the first 2 coming from section 1 and the third one coming from section 2. And let's say in the embedding space, the closest chunk to the question, what is self-attention, is chunk number 2. So the easy way we can go around that is that this chunk 1, chunk 2, and chunk 3 are actually very small chunks. So we pinpoint exactly a very relevant sentence in our document. But instead of sending this chunk to the language model, we will actually send the whole section 1. So it doesn't have to be a section, right? It should be some kind of a parent structure. Maybe we go sentence, paragraph, subsection, section. It can depend and vary depending on our data domain, how we decide on this hierarchy. But the main idea is, okay, let's have small chunks when we look for information. But when we will actually provide the notes to our LLM, we will not provide a single paragraph. We will provide the whole page or the whole section that contains this paragraph. And this will help because then LLM will have a bigger context and will be able to answer our question in a more precise manner. So this was the first technique I wanted to talk about. The second technique is leveraging the metadata. So when I'm talking metadata, I'm talking about document metadata. And let's say, in our case, we have N different papers on machine learning and NLP. Apart from the actual document texts, we may also have some metadata describing those documents. In our example, it may be things like, title of the paper or author or year or the topic and so on and so forth. So there may potentially be many attributes that describe those papers. In some commercial settings, you may say, okay, but I don't have any metadata on my documents. I have those 300 word documents that describes our products, but I don't actually have any metadata. They just raw. Well, first of all, metadata can start as simple as the file name or path. Maybe there is some kind of a fold structure that says smartphone descriptions and then documents about smartphones, and another folder that says tablet descriptions and then documents describing the tablets. So this is something you can already leverage because you can say, okay, these documents have a metadata attribute called smartphone, and this data has metadata attribute called tablet. And sometimes even the file name already contains some kind of information about the document, maybe the title of the document or, the model of the smartphone we are talking about. So you can already extract some useful information from that as well. And on top of that, what you can also do is, of course, nowadays you can also ask a language model to produce those attributes. In a more classic NLP world, you can also do topic modeling and feed your text into a topic model, and then it maybe extract 10 topics that have been discussed in that document. You can also do it with LLMs. You can ask, okay, extract me a number of different attributes that you would characterize this document as, and then maybe you will get a nice list of values in return that you can then use as metadata. So even if you don't have anything, you can still extract something automatically. You don't have to do this manually. Now, when you have this metadata, there are two things you can do with it. The most straightforward thing is that you can leverage those metadata attributes as filters. So imagine when I'm asking what is self-attention, I can also put a filter as a user. I can say only use the papers with the title "Attention is all you need," for example, or only use papers that are after 2017. This helps because this reduces the search space, right? We don't now need to look through all of our text, through our full textbook with notes. We just need to look at a particular set of pages that contain this filter. But the problem is that, of course, as a user, we don't want to specify those filters always, right? We just want to ask a question. We don't want to look through the list of filters and assign the values to them. It may cost too much time if we want to answer many questions. So another thing we can do with our metadata, we can simply include some of the most important metadata values as part of the text chunks that we are embedding. So you can notice this, how I illustrate this on the slide. On the left-hand side, this is a chunk without metadata. And on the right-hand side, this is a chunk that also contains the metadata essentially as a string that is appended to the chunk text. Why does it help? Well, imagine I'm now asking what is self-attention. You see that in the right, the attention is not only mentioned in the text of the chunk, but also in the metadata in the title of the paper. So this means that probably the weight of this chunk, or like when we embed this chunk, this values of the vector will probably get even closer in the embedding space to any question that also mentions attention. And this will help to pinpoint this particular chunk, sort of giving it higher weight compared to the documents that in the title don't say that they talk about attention. So what it means is that if there is some potential information in your metadata attributes that contain also similar or related terms to what you are searching for, this will probably help you to pinpoint those chunks better when you do the search in the embedding space. And that would be technique number 2. So if you have metadata or if you don't have metadata, generate it and try to make use of it when you're ingesting the documents. Great. The third technique I would like to talk about is also a kind of technique that combines the best of both worlds. And I will explain what worlds I'm talking about, and it is called hybrid search. So what hybrid search means is that we are combining two methods or two approaches to do the search, namely the vector-based search and the keyword-based search. So vector-based search is the kind of search that I was talking about previously when we do the embedding of the question, when we do the embedding of the source documents, and then we find the documents that have the closest distance in the embedding space. So this is based on the semantic meaning, right? Because we are embedding those values. So even if I ask what is self-attention or what is attention mechanism, arguably the embedding values of those two questions will be very similar. So it doesn't matter particularly how I phrase this question. The embedding sort of conveys the semantic meaning of the question that I am asking. Keyword-based search is something that was mostly popular before the field came up with semantic vector-based search approach. And this is just lexical search, meaning that given a query, what is self-attention, we can just search for matches of the word attention or self-attention. So we are just manually going through the text, and then if we find the word attention, this will be a match. And if we don't, this will be a no match. So this is just a lexical one-to-one search across the keywords that are in my user query. And if you think about it, it seems that semantic search, so vector-based search, should be a superior type of approaches, right? Because here we are not only looking for a perfect match of words, we're actually encoding them as embeddings. So we should be able to, reflect the semantic meaning of that context. We don't need to rely on 100% one-to-one match over words. But how it turns out in practice is that in some cases, keyword-based search may actually be useful. Imagine, for example, that our documents, and as a case in our example, contain a lot of domain-specific syntax or abbreviations. Let's say our documents contain a lot of abbreviations like RAG, LLM, and other things that are very specific to this domain. If our embedding model that we use to convert our user queries to embedding values, if it has not been trained on data with such abbreviations, with such terms, it will be very hard for it to come up with a meaningful vector value for those terms. It will, of course, create some kind of value, but it will not be able to match those values very well with what is contained in the other documents as well. Imagine that you have documents mentioning RAG and retrieval augmented generation using either abbreviated version or non-abbreviated version, right? If your embedding model has not been trained on such terms, it will not understand that. So it will probably encode this word somehow, but you might not be able to find a very accurate match when you look for those values in your document space. So what you can do basically to make use of that, you can combine both vector search and keyword-based search in your search pipeline. So what it means is that now when given a user question, so let's say what is self-attention, we will actually be looking at two search pipelines that we run in parallel. One of them will be, let's embed the user query using our embedding model, and let's find the closest chunk in the embedding space. And in this diagram, it would be chunk number 1. But in parallel, let's also extract keywords from our user question. In this case, it will be, for example, attention or self-attention, and also do a lexical search, do a keyword-based search over our chunks. And maybe in this case, chunk number 3 will be the most relevant chunk. And now we can go back to our LLM and show it both chunk 1 and chunk 3 and ask it to answer our user question. In that way, it helps us to not miss out on these documents that may not be found by the embedding model approach. So now we will not only have chunk 1, but also chunk 3 in the notes that LLM will read through before answering the question. And this is technique number 3, doing hybrid search. Great. Moving on to the next technique, number 4, which is called query rewriting and expansion. This has to do with a different problem that also comes back to the poor retrieval accuracy. But the underlying problem is that as a user who uses those conversational assistants, we are not always very good formulating our questions in a very specific, precise, and concise manner. So let's say we want to ask what is self-attention, but in real world, since this interface, those systems usually have a chat interface that make it look like you are chatting with your assistant, and you are feeling maybe yourself a bit less casual, and you are not feeling yourself as needed to formulate this very specific formal query. Maybe you are asking something like you can see on the slide, for example, hey, can you tell me about self-attention? I'm struggling to understand it. How does it work? Blah, blah, blah. So you can imagine that some users are not, can be asking more informal questions that also include a lot of noise and a lot of words that are not relevant to actually search for. Another use case is when we have the conversation chat, and then I might be, as a user, asking a follow-up question. So maybe my first question was about, can you explain me how computer vision models work? Then the system provides some kind of an answer, and then I'm asking, what about attention? Or what about self-attention? So this is not like a full question, because it is based on the context of the previous conversation. The problem is that if I just take the question, what about self-attention? Or if I just take the question, hey, can you tell me about self-attention? I'm struggling to understand it. I would like to learn about it. So let's imagine we embed this word to word exactly as how the user asked it. If we do this, then in some cases, we either don't have the relevant information in our question because the user omitted some of the words, which should be clear from the previous context, but are not clear from this particular message, in isolation. Or, like in the example on the slide, our question has a lot of noisy words that are not relevant. So if we start embedding that, this will be not as specific as it would be if the question would be just describe self-attention, right? And in this case, it can also lead to retrieving wrong chunks, not finding the correct chunks of text in this large embedding space. Remember, in my example, we're just talking about 10 documents, but in a typical commercial use case, we might have hundreds or even thousands of documents that describes different things in our system. And we simply, by having a bit of noise, we can diverge quite a lot in this embedding space and not being able to pinpoint the relevant chunks. So what can we do about this problem? Well, we should reformulate user question into a better structured search query. So one of the ways we can approach this, imagine that we have not a single language model call, but actually two language model calls that are happening sequentially when we answer the user question. So the first LLM would not need to answer the question, but the task of this first LLM could be to reformulate the user question into a specific and concise search query that we can then execute against our retriever and find the relevant chunks, right? So given a user question, I can ask a language model to rewrite it. And let's say the language model would rewrite this question into self-attention definition, which is a clear and concise query. And then we embed not the original user question, but we embed this particular query produced by the language model before we do the search in the embedding space. When we do the search, we retrieve the relevant chunks, and when we go back to the language model the second time to actually produce the answer, we will not ask this reformulated question. We will ask the original user question, but we will present the chunks that were found by embedding the reformulated user question. That way, we are still answering the original question, but we are sort of changing our strategy to find the most relevant paragraphs in our textbook. And rewriting is one of the ways you can go about it. A bit more sophisticated way is also called query expansion, where instead of just rewriting this question once, you can actually come up with multiple potential search queries that you can execute. So let's say we can ask our LLM to formulate 3 different search queries based on the question of the user. And it can be self-attention mechanism, attention explanation, what is self-attention? So it can be different alternative ways of formulating the same question, but they are a little bit different. So the embedding values of each of those queries would be a little different from each other. And then we can just execute those search queries one by one. Or, I mean, we can do this, of course, in parallel and find the most relevant chunk to each of those queries instead of just doing one of them. And then we can combine them and again show them to our language model as nodes when it tries to answer this question. And in that way, we are hoping that if we use multiple ways to ask the same question, and if we use multiple and different embedding vectors when we search through our search space, we are increasing our chances of finding the most relevant paragraph that actually contains the answer. So this is how we can do that with query expansion and query rewriting. Great. I think we covered the technique number 4. So now let me switch to the last but not least on my list is the technique called document reranking. So this doesn't have to do with the documents that we actually retrieved. We are assuming the retrieval strategy is staying the same. But once we have those documents, And once we show those documents to LLM as nodes, let's say we have 3 chunks of text that we retrieved on the first step, it does matter in what order do we show them to the language model. If there are many different paragraphs, right? On the slide, I have just 3 chunks, but imagine that we are actually retrieving 100 chunks and let LLM read through them. There are different studies that show that language models usually pay more attention to the first and the last positions of the text that you feed them, and whatever comes in the middle may be a bit omitted when the LLM is answering the questions. There are different techniques how to address that, but as a general rule, it is more likely that the answer will be more accurate if the relevant paragraphs are among the first paragraphs that you send to your language model. And then the problem may be is that when we retrieve the documents using this embedding similarity approach, the documents or the chunks will be ranked by those cosine similarities, let's say, between the vectors, which is a good measure, but may not necessarily be the best measure to actually reflect how relevant this paragraph is for answering this particular question. It may be that we are only showing to LLM the top 5 paragraphs, but actually the paragraph that contains the answer was the 6th paragraph, and we missed that because we ordered our documents by the cosine similarity, and we didn't want to show the whole textbook that we have to our language model because simply maybe it doesn't fit into the context, or it's too expensive to feed this 100 chunks of the documents to the language model. So you have to eventually select a certain number, like 3 or 5 paragraphs that you would like it to read. And in this case, the ordering does matter because, as I was saying, it may be that the answer is actually in the 6th or 7th paragraph, and you may simply miss that if you limit the number of paragraphs you send to a language model. So what you can do about it? One of the things, well, basically the answer to that problem is trying to re-rank the chunks of text after you have already retrieved them. Let's say we retrieved the chunks and now we are having this ranked list of chunks and we want to actually change those ranks to rearrange some of these chunks in the list. The question is how to do that. And there are multiple techniques, but one of the popular ones is, again, leveraging the language model for that. So imagine again, instead of a single language call, we actually have 2 calls to the language model. And the first call is just asking not to answer the question, but asking to re-rank the paragraphs or the chunks of text before we answer the question. So we are given the user question and we are giving, let's say, 3 chunks of text that we retrieved. We can ask the LLM to re-rank them and explain that we want the ranked list to be dependent on how relevant are those chunks to answering this particular question. And it may be that, the first chunks that mentions attention 10 times, but actually doesn't explain how attention works. It may be that the LLM actually then ranks this chunk last because it's not super useful. And another chunk that only mentions attention once, but does provide actually a detailed description of the inner workings of the mechanism, it will get ranked higher because now LLM is able to make sense of that and to say that the chunk 2 should come first, chunk 1 should come second, and chunk 3 should come the last. And then after we get this re-ranked list, we can again do a call to a language model actually answering the question, but now only using the top chunks from the re-ranked list that we got from the previous step. So this is a simple way how we can build that. And there are specific models that are trained specifically to do the re-ranking that we can use on this re-ranking step instead of actually just simply asking the language model. So there are different techniques. I don't want to go into a lot of detail since there are too many of them, but the general idea is, let's try to re-rank the documents. And one of the things that we can do, for example, we can retrieve a bigger part of documents initially and then ask to re-rank them and then limit again to the top 3. So let's say we retrieve top 6 documents, we re-rank them, and then we only from the resulting re-ranked list are only taking the top 3 and then trying to answer our question based on this top 3 chunks. This is how re-ranking works. Right. So that was the end for the 5th technique. that I wanted to share. As I mentioned, there are many different techniques out there. So these are just 5 that are popular and established in practice and tend to work quite well in terms of improving the retrieval quality based on my experience. If you look at the literature and blog posts, you will find many different papers, and this is maybe just an example reference for those of you who are very curious about learning more about some of these techniques. So although this is all very fresh and very new, this is an example survey paper that goes through, I think, more than 20 different techniques and tricks that can be applied on different stages. I covered the 5 that are established and proved to be working well, but there are many more you can explore if you are curious about them. Great, and I think with that, I'll just put on a slide listing all of the 5 techniques for on a background for reference, and that would be everything I wanted to share, and would be happy to answer any questions.
Yeah, thank you, Nikita. So we have a lot of questions, but I want to use my kind of privileged position, let's say, and I also have questions, and I think I also I've seen similar question in the chat. So, like in traditional machine learning, what we do, let's say I am training a churn model, right? So I have my XGBoost, then I have my data, and then I set up my cross-validation framework, right? And then I tune AUC, right? And then I play with different parameters, and then I see like whatever combination of parameters leads to better AUC, then this is the model I use, right?
Yeah.
And here, like we have a similar thing, like there are so many parameters, like with all these 5 techniques, like there is number of chunks we use, like the way we go from small to big chunk, the way we include metadata matters, the order of chunk matters, the size of these chunks, the number of chunks, the prompt we have, like, so the things we need to experiment with is like just the number of them is enormous. Like how do we actually come up with the best combination? Like is there a validation framework we can use for evaluating those parameters?
Yeah, so that's true. There is a very big search space and parameter space in here to try out. And this is a very good question because this is very important in practice, right? How do we actually learn whether it works or not? What is the best way to do it? It is a bit more challenging in the generative AI domain to do reliable validation of the results, but there are some attempts and some nice attempts to make it more structured. So in particular, regarding those RAG systems, there are some evaluation frameworks that allow you to actually do the evaluation of the system quality, also distinguishing between the performance of your retrieval component and the performance of your generation component. One of the popular evaluation approaches is called RAGAS, RAGAS. You can look it up, and the idea is that there, let's say, we can, as a company who wants to introduce this system, we can come up with a list of 100 questions. So imagine we set up an Excel sheet with a list of different questions that we would like our assistant to be able to answer. And when we start, when we deploy the system, we start to evaluate it. We start going through this list of questions and recording what answers it provides and recording what were the paragraphs of texts that we retrieved on the retrieval stage. And then having this information, maybe we can evaluate some of the metrics based on this information. So if we have enough resources, we can actually come up with ground truth answers for each of these questions, or we can come up with ground truth documents that contain the answers for these questions. And then if we know that, we can actually calculate metrics like precision and recall across the retrieved documents. So we can say, okay, on my 100 questions, in 60 out of 100, I am able to find the relevant document that is marked as relevant. And then if I change some of the parameters, I can see whether my precision recall metrics are changing or not. So it gets us sort of back to similar to like a classic ML approach, where as soon as we can calculate those metrics, we can start experimenting and testing different variants.
This way we evaluate our retriever, right? But then the architecture includes other things. So if we're
Yes.
interested in evaluating the answer, not necessarily the retriever, there should be something else. So let's say I come up with a gold standard data set, ground truth answers, right? So it can be me myself writing the answers, or let's say maybe we have already some sort of Q&A data set, like questions from the users and answers from the users from, let's say, Slack, right? Mm. How can we utilize this ground truth data to actually evaluate the answer?
So the easiest approach would be to use metrics like BLUE, for example, where you can sort of calculate the intersection, the word intersection between the ground truth answer and the LLM answer. And metrics like BLUE are commonly used in translation tasks, for example, when we need to evaluate the quality of text translation. But in some cases, there are many ways to formulate the same information in different ways. So one of the very popular things is to leverage an LLM for evaluation. So you can send to an LLM a separate LLM that doesn't know anything about our system, our context whatsoever. You can send two sentences. The first sentence will be the ground truth answer, and the second sentence would be the answer that your conversational assistant provided. And then you can ask the LLM sort of, are those two answers similar? Does the second sentence cover everything that the first sentence mentions?
Makes sense.
And
Yeah.
if it answers yes, then you put a checkbox. And this is what this Ragas framework do. It contains like a couple of prompt templates to do this automated evaluation. And then, after you deploy the new version of the system, you can just run this 100 questions and get some kind of metrics and get an impression how it performs.
Yeah, awesome. Thanks. Then if you don't mind, I'll share my screen because there are questions, and then
Of
maybe
course.
it's easier for you if I share my screen. So we'll just stop sharing yours. Do you see the question?
Yes.
Okay. So question from Max. What is the best way to combine system prompt, context, and user query to the final prompt?
Yeah, that's a good question. So this is
So maybe
in
before we answer this, so I'm just wondering, so system prompt, context, and user query. So user query, this is what the user types in the chatbot, right? What is system prompt and context?
So context would be the chunks that we retrieved, so our document snippets, and the system prompt is usually a prompt that contains some high-level instructions. That, for example, you are an AI assistant, you need to answer human questions accurately and fully, and so on. So some kind of high-level instructions.
What we do after we do the retrieval. So after we retrieve the potential documents that contain the answers, let's say 5 of them, we feed them into an LLM again, and then there is a prompt.
Yes.
Right? This prompt combines the user query, the context, the chunks, and then there is like an extra bit of instruction what the LLM should do with this information, right?
Yes, exactly. And it's hard to be generic because actually the answer to this particular question will be dependent on the LLM that we use. And so there are many different language models, right? There are closed source models like GPT, like Anthropic Claude, like other things. There are open source LLMs like Mistral, for example, and Llama 2. And all of these models have been trained on slightly different formats of instruction data. And all of these LLMs expect slightly different structure of the prompt template. For example, for Claude, for the most recent Claude models, it was shown that it is more beneficial to first provide the context and then ask the question. So the question comes actually out after the context. The first LLM needs to read the context. But in some other cases, it should be the other way around. And there is no good answer to this. You just have to experiment. You have to experiment with different prompt versions and then just see what version demonstrates the best performance.
So again, we need to have this evaluation framework like Ragas or something like that, right?
Yes, that's very important.
Because I think when I use ChatGPT, I usually put the questions first and then all the context, like based on this snippet of code. change that and then I copy paste the code.
Yeah.
Right?
I think usually each model provider now has a website with some kind of prompting instructions and guidelines that we can check out, and depending on the model, some of them will be more useful.
The question, when do you make use of fine tuning to make a model more specialized, and when you use RAG?
Yeah. So basically, fine tuning is an alternative to this approach, the whole retrieval step, right? Another option we can say, okay, let's just take our data, fine tune the model, and it will answer our questions well out of the box without any retrieval step. Uh, the biggest problem with that, and the biggest reason I think in practice to go for RAG instead, is that with fine tuning, you will probably not be able to incorporate the most recent information. So imagine if we are producing smartphones and if we are releasing a new device every month, then we will have to fine tune our model again every month. And this will of course be costly because those models are big. You need a lot of GPUs to do the fine tuning. And in this case, it will be more costly to do the fine tuning repeatedly compared to the RAG case where you can just add a new documents to your knowledge base and it starts working immediately. So probably if your use case is very static, so the data does not change, you just need your model to become an expert maybe in Harry Potter universe, for example, then maybe you can just fine tune a model based on those Harry Potter books and not do any RAG. But if your data is dynamic and can change, I would go for RAG.
And I guess you also need a certain amount of data to be able to do fine tuning. While with Harry Potter, there is already how many books? 7, right? Like
I
there's
think, yeah.
yeah. Or like one of them is actually 2. It's movies. Anyways, like there is a lot of information, right, that you can feed into an LLM, like all these books, movies, fun sites, whatever. But like, let's say this is a very niche topic and there's not so much information, then fine tuning might not even make sense at all. Like the model will not see enough data to change the weights.
Exactly, exactly. And you are not able to fine tune just any model, right? Fine tuning would be possible with some models, with some other models it is not feasible. And imagine a new model comes out next week and you cannot fine tune it. But if you use RAG, you can immediately plug it in, just change your API call. But if you rely on fine tuning, you would not be able to quickly adjust because you would need to actually be able to fine tune this model.
It looks like RAG is the way to go, but like let's say with Harry Potter, does it even make sense to try fine tuning? Should we go directly with RAG?
I think in most cases we should start with RAG and see how it works. I would imagine maybe in some cases still fine tuning can be useful, but based on my experience, my default approach would be to try RAG first and see if it can deliver. Probably you can improve your retriever so much that you don't need to fine tune the model. You will always be able to provide it with relevant paragraph from the Harry Potter book, and in this case, you don't need actually fine tuning.
Do you have a bit more time or you need to go now?
Yes, I can answer a few more questions.
Yeah, I think we started with that. So this is what I asked you about evaluation. But the question actually goes on, and so backfeed loop, I guess this is what we talked about, like how exactly we structure our evaluation validation framework. But what about these hallucinations? Like how do we fight hallucinations in this case?
Yeah,
How do we evaluate while knowing that model might hallucinate?
yeah, yeah. This is a big topic. Hallucinations in language model, right? And in some sense, it's a feature, not a bug, because we want our models to come up with words that are not just citing the source one to one, but in a certain sense, all output that the language models produce are hallucinations. But what we want this output to be true, to be correct, to be relevant based on the documents and information that we provided. So to avoid hallucinations, I mean, RAG in general is one of the great tools to avoid hallucinations because what you will see is that when you provide those right contexts, right pieces of information, the language model hallucinates much less frequently compared to a case where you just ask those questions without any references, any context that you provide to it. So first of all, it's about using RAG and about modifying your prompt template to ensure you instruct the model to only use the information provided. Do not come up with stuff based on your internal knowledge, for example. And to instruct model, for example, if you are not sure about the answer, please say, I don't know, rather than coming up with the answer. So you can modify the prompt templates, your system prompt, your instructions, to make sure the model knows that it is expected to say, I don't know, or it is expected only to use the retrieved context. And on the evaluation stage, of course, this comes back to what kind of metric are we using. So in this RAGAS framework, one of the metrics we can use not on the retrieval stage, but on the answer quality evaluation stage is, I think, called answer truthfulness, where we show the answer and the context to another LLM and ask, is this answer actually based on the context? Yes or no? And if this post-processing check says no, then maybe we actually run it right away before we show the answer to our user. And if this post-processing check says no, we will not show our answer to the user. We instead say a placeholder that says, I don't know. So this is something we could do, for example, in production. But of course, this would involve an additional call to LLM, which may cause a bit of latency. So we may think whether to integrate it or not. But in any case, this is how we can evaluate the output.
And I also noticed with ChatGPT, when you ask it to do some sort of rewriting or summarization based on something, then it usually works pretty well. But when you just ask it a direct question, that it might come up with something.
Exactly.
How do you know that rewriting by an LLM is actually better than the original query?
Yeah, I mean, again, we talked about evaluating, right? So we can get recall and precision values for our retriever. Let's try with and without rewriting, run it through 100 questions and see whether precision and recall get better.
Okay, so here we focus on a single component, not
Yes.
like the whole architecture. We just evaluate the retrieval part, and we use the standard information retrieval metrics like precision and recall.
Yes, exactly. I think it's important to, when we can focus on a single component of the system because, of course, we can evaluate the resulting answer quality as well. But, under assumption that retrieving better information will lead to at least not worse answers, but probably better answers, we can focus on the retrieval because it's maybe easier to evaluate, and then just evaluate that part.
Yeah, let's take the final question. So is the retriever holding the most of the knowledge on the topic while the LLM is only doing some cosmetics like changing the text and so on?
In some sense, you could say that. I wouldn't say it's just doing cosmetic. I would say it's also about connecting the dots and aggregating the information from different paragraphs, right? If you retrieve 5 paragraphs and they all talk about attention, you need to actually aggregate this information and provide a concise and relevant answer. So it's about, basically interpreting those notes, aggregating it, and a bit of styling to match the user question and providing the answer, but not so much about the internal knowledge of LLM about the world that it learned during the pre-training process. It may use this knowledge to fill in some of the gaps, but the important point is that we try to have our retriever coming up with the most information to make this task easier for an LLM. This is what it is about.
And not all the chunks actually contain the answer, right? So
Exactly.
so needs to decide, okay, this one is not relevant, I'm just not using it, but this one is relevant, this one is also relevant, let me combine the information from these two.
Yes, true.
So I remember on your slide, there was a link to your website. It's your last name.me, right?
Yes, so it's kozodoi.me. It's my website. It also has links to my social media and my some of my blog posts and other talks. So please feel free to check out if you're interested. And you can reach me out on LinkedIn if you have more questions, for example. And you can find my LinkedIn profile is /Kozodoi, or you can also find the link on my website as well.
So good that Zoom includes the last name, and it's also in the title of the YouTube video. But you can also send us all the links, and we will include them in the description. So thanks everyone for joining us. Thanks Nikita also for sharing all your knowledge today with us, answering all these questions. Yeah, thanks a lot. It was very interesting. And yeah, I guess that's all for today.
Yeah, my pleasure. Thanks a lot for inviting, and wishing everyone nice day ahead or evening.